Hello everyone. Welcome to DD Science and you are watching our program The Maths Factor. Today is all about prime numbers. We are going to explore how primes are the building blocks of all numbers. Cicada, they usually make noise to attract gnats or cause an alarm. But how they know primes? Can primes protect our credit card payments? So join us in our excursion through this magical subject. Keep watching. It's going to be quite a journey.
Amrita is lazing around, reading The Curious Incident of the Dog in the Nighttime by Mark Haydon. This book is about a young boy called Christopher John Francis Boone, who describes himself as a mathematician with some behavioral difficulties. In this book, he tries to solve an unusual crime and records his progress in a novel. Instead of numbering the chapters 1, 2, 3, etc., Christopher numbers them 2, 3, 5, 7, 11, 13, so on. Can you see the pattern? Right. These are prime numbers. In fact, Christopher's fascination with prime numbers comes through in the lines. Prime numbers are what is left when you have taken all the patterns away. I think prime numbers are like life. But before we set off, let's quickly look at what a prime number is. Take the number 21. We can divide it by 1, 3, 7 and 21 without leaving a remainder. Now take 23. We can divide it only by 1 and 23. 23 is a prime. 21 is not. Quickly look at what a prime number is. So prime needs to be greater than 1. Its only factors are 1 and the number itself. Let's look at some other numbers. Start off with 1. The definition says greater than 1, so 1 doesn't qualify, though once upon a time 1 was considered a prime. Take 2. What are the factors of 2? 1 and 2. Meets both arrows, so 2 is a prime. Now what are the factors of 3? 1 and 3. So 3 is also a prime. What are the factors of 4? 1, 2 and 4. So 4 is not a prime. Non-primes are also known as composite numbers. Now all even numbers except 2 are clearly composite. Going forward on primes, 5 is a prime. 7 is also a prime. Does that mean that all odd numbers are primes? Let's take 9. The factors are 1, 3 and 9. So 9 is not a prime. So the opening list of numbers of primes are 2, 3, 5, 7, 11, 13. Now let's get back to the number 1. It is neither prime nor composite. A bit like a VVIP, it is usually placed into a class of its own. With 1 excluded, the smallest prime is 2. However, 2 is the only even prime. Now, let's move to the story of how cicadas understand primes. Quiet. Just listen for a minute. Can you hear the chirping sound? It's the cicada. They usually make this noise to attract mates or cause an alarm. There are many kinds of cicadas, but the one we are interested in the periodical cicada, because they seem to have intuitive understanding of primes. Seems unlikely. Well, hear me out first. The cicada incubates underground, which means they remain underground while they're growing from a larva to a full-grown adult. And this can take a very long time, sometimes 13 years and sometimes 17. To survive this, cicadas have adapted to an extent that they can sip juices from plant roots while underground and come out fully prepared to take on the world. Now, have you spotted the prime connect? Yes, the number of years they incubate, 13 and 17, are both prime numbers. For a long time, people dismissed this as coincidence, until Stephen Jay Gould, an American paleontologist and evolutionary biologist, came up with the theory that primes help protect cicadas. For example, if cicadas emerged every 10 years, their emergence would coincide with predators whose life cycles neatly divided into theirs, which would include ones that had 1, 2, 5 and 10-year life cycle. Similarly, if the cicadas emerged every 15 years, they could fall victim to predators with 1, 3, 5 and 15-year cycles, which are all the factors of 15. Now, when they come out in prime year cycles, there is less chance, since there are less factors of predators emerging at the same time. All in all, primes help cicadas survive. Now, primes have fascinated mankind through the ages. Arvind is in the library reading up on this. He reads about Eratosthenes, who was the head librarian in the famous library in Alexandria, Egypt, over 2,500 years ago. Among many other things, he worked out a way of locating prime numbers. The method came to be known as the sieve of Eratosthenes. Arvind tries to see how it works. He lists out the numbers 1 to 100. He first crosses out the 1. 2 is a prime. He leaves it, but crosses out all multiples of 2. This also covers all multiples of 4, 6, 8 and 10. He then crosses out multiples of 3. This would cover multiples of 9 also. He then moves on to multiples of 5. Clearly all the multiples of 10 are also deleted in this process. He then crosses out all the multiples of 7. We are now left with only primes. What Arvind has done is cross out all the multiples of numbers till he reached the square root of the largest number in the grid. In our 1 to 100 grid, the largest number is 10, so he's crossed out all the numbers until 10. 11 onwards, he doesn't need to do.
Let's take a break now, but we will be back to explore the endless patterns these primes can form, how primes are building blocks of maths, and meet mathematicians who have been fascinated with these magical numbers through the ages. Welcome back to your favorite show, The Maths Factor. Today, we are exploring the world of prime numbers. The primes are the atoms of the number sequence, and all other positive integers are built from primes. But how? Take a look.
Now, mathematicians have always been fascinated by primes because they are considered to be the building blocks of all numbers. Like atoms, are the building blocks of all matter. Now let's explore how that is literally true. Let's think about this a bit. Look at our first 9 digits. All these are either prime or primes multiplied together. We could keep going on in this vein. To check if this is true, let's take any random number, say 78. Now we can write it as 2 into 3 into 13, all primes. And this factorization is unique except for the order of primes. Let's try another number, 84. 2 into 2 into 3 into 7. Again, a unique factorization of primes. So what we've figured out is that every number is either a prime or it can be made by a unique product of primes. This idea is called the fundamental theorem of arithmetic. Let's return to Arvind, who is now looking at patterns in primes. When he looks at the primes under 10, he notices that 4 out of 10 are primes, which translates to 40%. 25 out of the first 100 numbers are primes, which implies the frequency of numbers under 100 are 25%. Now, in a similar fashion, the frequency of primes under 1000 is 16.8%. He deduces that the frequency reduces as we proceed into higher number zones. This makes him wonder, Will we run out of primes as we head into extremely high number zones? There's an answer to this. And for that, we'll need to meet up with a famous Greek mathematician called Euclid, who lived way back in 300 BC. What Euclid figured out was, if you think of one prime, there exists a higher one. Arvind tries to track his thought process. What Euclid did was he first assumed that there were only a finite number of primes, P1, P2, P3, all the way up to Pn. Now, P1 into P2 is not a prime since P1 and P2 are factors. Similarly, P1 into P2 into P3 is not a prime. So, P1 into P2 into P3 all the way to Pn is also not a prime. Now Arvind creates a new number, P, which is basically P1 into P2 all the way to Pn plus 1. Now we have two possibilities, that P is a prime or P is not a prime. If P is a prime, we have a new prime right away, which means there are not a finite number of primes, there is one larger prime. And our proof is complete. However, if P is not a prime, it must be divisible by a prime number, according as the fundamental theorem of arithmetic that we just saw. Let's call that number R. Now R can't be any of the numbers P1, P2 all the way to PR from our original list, because if you divide them by P, you will get a remainder 1, which means P is not divisible by any of these prime numbers. So R is a new prime. Whichever way you choose to look at it, either you have found a new prime P, or if P is not a prime, then R is a new prime. So what Arvind has worked out, like Euclid, is that there is always one larger prime. Now, if there are loads of primes, it follows that there are some enormously large ones. We're going to explore how useful these are later in this episode. There is a constant search for large primes. The longest one so far was found in 2013 by Curtis Cooper from Canada. The number has 1,74,25,170 digits and would be about 16 kilometers long if written. If we presume it takes a second to write 3 digits, it would take more than 67 days to just write down this number. In fact, it took a supercomputer 39 days to even prove that the number was prime. Now, this idea of prime numbers being the building blocks of all other numbers became even more tangible with a conjecture by a mathematician called Christian Goldbach. Goldbach was born in Königsberg, which is in modern-day Russia now. He was a friend of many of the great scientific minds of that time, Leibniz, Bernoulli, Euler, to name a few. He and Euler corresponded, and in one letter in 1742, Goldbach theorized, every even number greater than 4 can be expressed as the sum of 2 odd primes. What does that mean? Very simply, take any even number, say 6. It can be written as 6 is equal to 3 plus 3. Similarly, 8, 3 plus 5, 60, 43 plus 17, and so on. He came up with a second premise, which says every odd number greater than 7 can be expressed as the sum of 3 odd primes. Let's see some examples here. 9 is equal to 3 plus 3 plus 3. 11 is equal to 3 plus 3 plus 5. It's simple enough to understand. Unfortunately, it's not easy to prove, because one broadly needs to keep testing till one finds a counterexample. Euler himself gave it a shot. He first managed to check it up to 1000 and then up to 2500. He wrote back to Goldbach with these results. Goldbach seemed quite content coming up with these ideas and leaving it to Euler and others to test. In fact, the seemingly simple problem still remains firmly on the to-do list of mathematical challenges to crack. Many attempts have been made, but a definite proof still remains elusive.
Right now, it's time for a short break. We will be back after the break, and then we will explore how primes are used in codes and encryption. So keep watching the Maths Factor.
Everything in this world is made up of tiny particles called atoms. At present, there are 118 different types of atoms. Most things have more than one kind of atoms in them, but certain things occur in nature in their purest form, with only one kind of atom, which is known as an element. For example, a lump of pure gold contains only one kind of atom. If we zoom into a lump of gold, we will find a number of gold atoms. Similarly, if we zoom in a lump of silver, we can see many silver atoms. Since there are 118 kind of atoms, there must be 118 elements too, one for each kind. Out of these, we come across many in our daily lives like carbon, iron and aluminium, but might have not heard about other elements like astatine and ytterbium. With so many elements, there are a lot of names to remember. Fortunately, there's a list showing all the elements. It starts with the element with the lightest atoms, that is hydrogen, and ends with the element with the heaviest atoms, which is uranium. This list is called the periodic table. It describes the atomic properties of every known chemical element in a concise format, including the symbol, atomic number, atomic mass, and relationships between the elements. In 1969, Dmitry Mendeleev, a Russian scientist, formulated the periodic law and created a far-sighted version of the periodic table of elements, which not only had the list of then discovered elements, but it also left space for the undiscovered elements as well. Year 2019 marks the 150th anniversary since Dmitry Mendeleev came out with the periodic table system, and UNESCO has proclaimed it as the International Year of the Periodic Table of Chemical Elements. There have been numerous modifications in the periodic table since then, and today it is one of the most significant achievements in science. Rather than memorizing facts and figures for each element, a quick glance at the table reveals a lot about the reactivity of an element, whether it is likely to conduct electricity, whether it is hard or soft, and many other characteristics. Once scientists and researchers understand this data, they can apply it in their experiments.
Welcome back to your favorite show, The Maths Factor. Why? Some smart people are spending their years to find a number which is not going to be divisible by any number. And how prime numbers protect your money and privacy. Take a look.
Now, mathematicians through the ages have been fascinated with patterns in primes. In fact, the famous Leonhard Euler once commented, "Mathematicians have tried in vain to this day to discover some order in the sequence of prime numbers, and we have reason to believe that it is a mystery into which the mind will never penetrate." Which brings us to the story of the Polish-American mathematician Stanislaw Ulam. Now, in 1963, he was at a conference listening to a long and very boring paper. Like many of us do, he started doodling. But instead of doodling funny faces, Ulam started working out patterns and primes. He started off by writing the number 1 in the center. He wrote the number 2 immediately to the right, 3 right above that, and then in spirals he wrote all the other numbers around 1. He then circled all of the prime numbers and an unexpected pattern emerged. To his surprise, the circled numbers tended to line up along diagonal lines, or as Ulam more carefully pronounced, it appears to exhibit a strongly non-random appearance. Since then, many logic grids have been run on computers, and the tendency for prime to group around diagonals has been confirmed. In spite of the mathematician's fascination for primes, There was no specific uses for them till the modern era, when suddenly that changed. Every time you use an ATM or buy something on the internet with your credit card, you use prime numbers to keep your personal information secure. Let me try and explain as simply as possible. It's through a process called encryption. But first, let's see how codes work. Ayushman and Mahira are studying under the watchful eye of their mom. Now Ayushman wants to let Mahira where the laddus their nani sent is hidden, without his mom catching on. So he writes, Nani's laddus behind fridge in code. He very simply assigns values to each letter. A is equal to 1, B is equal to 2, and so on. So here's what the message would look like. This is very simply encryption. Now Mahira decrypts the code, which means she decodes the message from coded text. And thus they're able to get a break from studies away from their vigilant mom. But how does that work on the internet? If I send my credit card number and PIN over the internet to an online bookstore, the bookstore should be able to read it, but no one else should. How can I ensure that? This dilemma was solved in 1978 by Revest, Shamir, and Adelman. Their method, now known as RSA, depends on some marvelous properties of prime numbers. One of these is that it is rather easy to generate large prime numbers, but much harder to take the product and reduce it back to its original primes. This is like the trapdoor, since it's a function that lets you go one way easily, but not the other, a bit like the famous Chakravyuh that proved to be Abhimanyu's downfall in the Mahabharata. He was able to go in one way, but was unable to exit on the other side. Anyway, in mathematics, such one-way functions are at the bottom of all public key encryption. Let me tell it as simply as possible. Bharat and Ahana are senior corporate executives. Bharat needs to be able to send confidential message to Ahana. Isha is a spy from the competitor's office and is constantly trying to access the confidential information. Now what Ahana does, which is very clever, is she chooses two prime numbers, P and Q, each more than 100 digits long. Now she multiplies the two primes and produces PQ, a still bigger number that is naturally not prime. This is Ahana's public key. It is open to public view. Anyone can access this. Now Bharat's PIN number is N. He multiplies this into PQ and sends it to Ahana. She knows P and Q, so she can decipher the message and process his payment. Now if Isha intercepts this message, she will not be able to decipher this, since breaking down PQ into P and Q and hence accessing N is actually enormously difficult. Putting aside Bharat and Ahana, what does this mean to us? When we send private information out, it gets encrypted as it travels, which means that it travels as NPQ. Only the intended recipient, who has the key P and Q, can decipher this information. And so, no spy will hopefully get their hands on any information.
That's all for today. We have explored the magic of primes. We have seen how to locate prime numbers, fun patterns in primes, and some uses. Who could have thought that just a number that is difficult to factor could fuel so much of our lives? And we have barely to skim the surface. There is much more to prime than this. Keep watching more episodes of the Maths Factor for out-of-the-box mathematics. Do not forget to send your views about the show. Please mail us at ddscience at vigyanprasar.gov.in. You can write back to us, Vigyan Prasar, A50, Institutional Area, Sector 62, Noida, UP 201309. For program schedule, you can visit our website www.vigyanprasar.gov.in.